This video is a quick little introduction to the idea of rotational work and kinetic energy. So it actually reviews a lot of the ideas that we learned about when we first learned about the work kinetic energy theorem. But a lot of times when you apply a force to an object, it could make it spin rather than just change its translational kinetic energy. And sometimes a force can do both. It can make an object spin and translate. So we'll start with the simplest idea where we're just and maybe have a pulley here. Some type of a pulley, could be the top of a lawnmower. It's maybe a flywheel or something like that, and you're pulling a string. And what you're doing is beginning to spin this pulley. And so as you apply a force to the string, right, then what's going to happen is the string is going to pull and begin to rotate this disc. And as it begins to rotate this disc will start to make some revolutions and it'll speed up. And so what will happen is it'll increase what's called its rotational kinetic energy. So the big idea starts with what we already know. So we have a work. We're applying a force through a distance. And in this case, the delta S, right, that the linear distance, delta S, or the string will translate, okay, delta S along here, translates to a rotation on the disk of the arc length, right? Because any delta S that's translated here is going to be r delta theta via the arc length. And that's how far the string will also be pulled. So it's pretty easy to realize that what we can do then is, if we want to think about things in rotational terms, just take our work term, replace the delta S with the r delta theta, and we know that this term right here, right, F times r is going to be what we recognize as the torque. So if we want to think about work done rotationally, we can also think about it in terms of as torque times the delta theta. Okay, where delta theta is going to be in radians. So that's another look at work when work ends up being in rotational quantities or translated to rotational quantities. Now remember we learned about the work change in kinetic energy theorem, where the net work of all of the forces applied to the object changes the kinetic energy of the object. So in this case, we're going to take the simplest idea where this pulley is pinned, okay, and so it's simply going to rotate and it's not going to roll along and translate forward at the same time. So in this case, what we can see is if we just think about kinetic energy in terms of pure rotational terms, 1/2 mv squared, you know, there'll be different linear velocities at different radiuses away along the edge of the wheel. So how can we express this in terms of rotational terms? Well, if we remember that when we talked about the velocity tangentially out at some part on an arc of a circle, it was r omega, the radius times the angular velocity. So if we just take that and say the r omega squared, or the v is equal to r omega, we can substitute that in as r omega squared. We end up with 1/2 mr squared omega squared. Now if you remember, if this was a point particle out here, maybe something along just a point mass along the edge, then our mr squared would be the moment of inertia for that point mass. But we can generalize that, and that I could be for any shape where there would be the k out in front of it. So if it was a wheel, or if it was a hoop, solid disk such as this, maybe it's a ball or something like that, we can generalize this mr squared term to any term I. Okay, and if we know the moment of inertia for that object, then we can say its kinetic energy when it's rotating is going to be 1/2 I omega squared. Okay, so that's kinetic energy for the rotational terms. Okay, so if we take a look at our work change in kinetic energy theorem when we do our net work on the object, we'd say we'd have the 1/2 I omega f squared minus 1/2 I omega I squared, which is just the final rotational kinetic energy minus the initial kinetic energy. So work, if it's only going to be applied in this case, that's just beginning to spin the object, this is our expression for the change in its kinetic energy. All right, we've got mass, right, we've got inertia, just like 1/2 mv squared, and we've got the square of the velocities. So we can apply that to a problem, right, using our work kinetic energy theorem, just like we did when we first learned about that. But the problem might be something like this one, where we're applying a force with a string out at the edge of this object. So what we end up doing is taking a look at how we can, see, let me get my shade back up here, and, oh, actually, I guess I don't need that anymore. All right, so if we have a string is pulled applying a force of 10 newtons at the edge of that solid pulley of radius 0.20 meters and a mass of 1.5 kilograms. So we could ask, like, what is the angular speed of the pulley after 5 revolutions, and what would the linear speed of the string be after 5 revolutions? So we're just going to apply the work change in kinetic energy theorem like we just saw. So we can take the work, and what we could do is we could say the work is going to be our torque times our delta theta, and that should change the kinetic energy. So we'd have 1/2, oh, I started writing mass out of habit, but in this case it's going to be 1/2 I omega F squared minus our 1/2 I omega I squared. So that's just the work change in kinetic energy theorem. All right, we know our torque is going to be R F, and then we've got our delta theta. So I'm just going to continue here. And now substitute in some of the things we know. So we know that the solid pulley, where that string is being applied out at the edge, was at a radius of 0.20 meters. Okay. And the string is being pulled with a force of 10 newtons. And now we know that we have to convert our 5 revolutions to radians. So we know that there's going to be, for every 5 revolutions, we know that there's 2 pi radians, right, for every 1 revolution. So we're going to have 10 pi in terms of our total amount of radians that the object's going to move through. And we're going to have our 1/2. So we have to remember I for the disk. So if you remember I for a disk, and we're going to treat that pulley like a thin disk, it's 1/2 mass of the disk, right, times the radius of the disk squared. So in this case, we're going to have the 1/2, and now we have another 1/2, which is due to the moment of inertia of the pulley. And the mass of the disk, okay, maybe I should write it all out here. Mass of the disk, radius of the disk squared. Okay, so there's our I term, right, omega F squared. And let's say the disk is going to start from rest, so its initial angular speed is going to be 0. So if we let omega I equal 0, beginning from rest, then we don't have that initial kinetic energy term. All right, so I'll just come in here, 0.20 times 10 times 10 pi radians. It's going to equal 1/4, and the mass of the disk is given as 1.5 kilograms for the pulley. And again, the radius of the disk is 0.20, and that should be squared. So we've taken care of all of these terms here, and what we're left with is our unknown, omega F squared. Okay? All right, so that gives us an final angular velocity of 64.7 radians per second. And then remember that the string was out on the edge of the wheel. So its linear velocity is going to be the same as the tangential velocity of the wheel. So that's just going to be r omega. So if we want that linear velocity of the string, it's the same as the edge of the wheel. So we can just take 0.2, right, times our 64.7 radians per second. And that gives us 12.9 meters per second, which is pretty fast. Okay, so that string's really going to be moving by that point after 5 revolutions. Okay, so that is just a real quick application of how you would apply work, to a spinning object in terms of rotational terms.